Have you ever wondered why radar sometimes sees small objects but misses the large aircrafts like these based on the stealth technology? It is due to the impact of radar cross-section of the target. S- So we have seen this factor in the radar range equation, which represents the radar cross-section of the target. So in this video, we are going to explore what is meant by radar cross-section. So the radar cross-section of a target is a measure of detectability of the target by the radar. High RCS means high detectability and low RCS means the low detectability of the target by the radar. It does not represent any physical size of the target. That means that it is radar cross-section of the target is not related to the physical size of the target. It actually represents the measure of the detectability of the target by the radar. So it does not have any relation to the physical size. So let's see that based on some analogy. So consider a mirror which is illuminated by a torchlight. Here you can see that as the mirror is illuminated by the torchlight, it will be getting reflected back as the mirror is the reflective surface. But if the same light is used to illuminate the wall or some buildings, we won't be getting any reflection back. So that means that the material actually contributes to the reflection of the light. So even these mirror and the wall has the same area. It does not mean that its reflectivity is same for the mirror and wall because it actually depends upon the property of this material which reflects back the light. So here you can see that as the mirror is reflective, it is reflecting back a lot of light, and in case of the wall, as it is not reflective, it is not reflecting anything back. So in that case, the reflectivity is more, and in this case, reflectivity is less. So similar thing happens in case of the radar cross section also. So this radar cross section does not corresponds to the actual physical area of the target. It actually represents the radar detectability of the target. That is how much that target can reflect back the power so that radar can see that object. So let's see more details about radar cross section in coming slides. Consider the case of the radar which transmits an electromagnetic wave and hits on the target, and based on the target's probability it will scatter the reflected power in different directions. Here you can see that some of the power is reflecting back to the radar itself and some powers are scattered in different directions. So these reflected powers actually represents the radar cross section of this target. So the radar, this is the definition of the radar cross section. So the radar cross section is a measure of power scattered in a given direction when the target is illuminated by an incident wave. So this is the IEEE definition. RCS is a measure of reflective strength of the targets, defined as 4 pi times the ratio of power per unit solid angle scattered in a specific direction to the power per unit area in a plane wave incident on the scatterer from specified direction. So in this case, we can say that whichever is power is reflecting back to the radar divided by the total power incidenting on it gives an indication about the RCS of the target. So if our observation point is here, the power reflecting in this direction divided by the total incident power gives an indication about the RCS. So the RCS of the target actually depends upon from where we are viewing the object. So if we view the object from here, the RCS will be different, and if we view the object from here, the RCS will be different. So the RCS actually depends upon the observation point and it gives an indication about the total reflectivity of the target in that particular direction. So this is the definition of the RCS of the targets. So let's see how it is derived. So we know that this is the total RCS, that is, it is a ratio of the scattered power to the incident power, and it has a factor of 4 pi r square. Let's see how this definition is evolved. So consider the electromagnetic wave having a transmitted power density of pi, which is incidenting on this target. So this is the target, and let's assume that this target has a radar cross-section area of sigma. So sigma actually represents the area of the target, which can in effect provide some reflection in a particular direction. So if the target has a RCS of sigma, that means that it will scatter the power sigma times the total incident power in different direction. That is, this is the incident power and the total scattered power will be sigma times the total incident power on the target. And we are assuming that this target is scattering the power equally in all the direction. That is, it is like an isotropic scatterer. So in that case, the power in a particular direction can be given by sigma pi by 4 pi r square. So this r is the distance between the target and the source. So we know that this 4 pi r square is the contributing factor when we are considering the isotropic scattering. So the total scattered power in a particular direction can be given by pi sigma divided by 4 pi r square. So this equation, from this equation we can calculate the RCS. So the RCS is based on this equation, and here you can see that if you rearrange this equation, we will getting the radar cross section. So the radar cross section equal to 4 pi r square PS by Pi. So in terms of the electric field, it can be given by the expression 4 pi r square E scatter square divided by E incident square, as the electric field is uh, proportional to the power density. So we know that based on the Poynting vector, the power density is equal to half E cross H, and as it is equal to E by eta, it will be corresponding to the E square. That is how this equation has evolved. So this is the basic equation to calculate RCS of a target. So this is how it is evolved. So let's see what is the unit of the radar cross section. So from previous presentation, we have seen that the radar cross section actually represents the effective area which can provide the reflection in a particular direction. So based on this equation, we can see that this will be cancelling out, and this RCS has a unit of meter square. So it in effect represents the effective area. So when we convert that into the logarithmic scale, the unit will be in dBsm. So decibel per square meter. So this is the unit of radar cross section. So in case of the monostatic RCS, we know that the transmitter and the receiver positions will be the same. So we have to only consider this backscattered power from the target. That is the reflected power from the target we have to consider. And when we substitute that, we will be getting the radar cross section of the target. So in the case of a bistatic target, we know that the receiver position is different. So we have to take this scattered power to calculate the radar cross section of the target. So the radar cross section of the target actually depends upon from where we are observing the reflected power. And let's discuss what are the different factors which will be affecting the radar cross section of a target. So if we are considering the geometry and the shape of the target, it will have an impact on the radar cross section. So in this case, if we consider a flat plate and some curved structures, this flat plate will be having the high RCS and this will be having the less RCS. So the shape and geometry will have an impact on the reflected power. Next one is the aspect angle. That means from which angle we are observing. So if we are observing the flat plate at normal instance, it will be having high reflected power. And if it is like tilted, the reflected power will be less. So the aspect angle will also have impact on the radar cross section. And it actually depends upon the material of the target also. If the plate is made up of the metal, the reflected power will be more, and if we are using some absorbing materials or dielectric, the reflected power will be less. So the material of the target also has impact. Also, the frequency of the electromagnetic wave that we use also has impact on the radar cross section. So let's consider two frequencies, 3 gigahertz and 10 gigahertz. If you have a very small targets, this target can be easily detected by the high frequency electromagnetic wave, and this small target is very difficult to be get detected with this 3 gigahertz wave. So the frequency also has impact on the radar cross section. So if you are considering a complex geometry like this, the radar cross section of these flight actually depends upon the observation point, the geometry that we are seeing. That means if we are observing from here, the geometry is different in this direction, the geometries are different in different directions, and it has different shapes in different angles. So all these depends upon the radar cross section of this target. So it is completely depending upon at which angle we are observing the radar cross section of the targets. Let's see some of the typical RCS that we are considering in some common examples. So if we are considering the stealth aircraft, this aircraft is like modified using some radar absorbing materials, and the shape will be modified to reduce the reflections from these structures. So it will be having a typical RCS of minus 42 minus 20 dBsm. So this is very less detectable using the radar. The bird has an RCS of minus 20 dBsm. The human child will be having an RCS of around minus 3 to minus 5 dBsm. Bicycle has an RCS of 3 to 5 dBsm. As we consider the car, we know that car has lots of metallic parts, so it will be having a typical RCS of 10 to 20 dBsm, and the commercial flight will be having an RCS of 20 plus dBsm. Here you can see the RCS difference of flight and stealth aircraft. By using the modifications, we can reduce the RCS of the stealth aircraft. So I hope you get some idea about what is meant by radar cross section and what are the factors affecting the radar cross section. Thank you so much for listening. If you find any of these videos useful, kindly support by liking, commenting, sharing, and subscribing. Thank you.